What are the 3 technological advancements that are shaping the future of mechanical design? Let's talk about those 3 things next. Let's talk about the fundamentals of mechanical design. Before we get started, if you want more guidance on technology-led initiatives, especially for engineering, follow us or subscribe to our channel to get more insights like this more frequently. So with that said, mechanical design, there was a big change back when computer design software kind of came out. It was a big state change for the approach of mechanical design because those capabilities were very powerful and they could allow engineers to do things they could never do before. We're now on the verge of the same type of state change in mechanical design. There's emerging technologies that are going to make a huge impact, open up a lot of new possibilities in terms of design, and that's what we're focusing on with this series. But first, let's talk about a little bit of context. It's important to understand what are the primary levers that mechanical engineers can pull today in terms of really making a difference with their designs. So let's take a look at that. When it comes to developing a mechanical design, there's really 3 things that mechanical engineers can do to kind of affect performance and capability and requirements fulfillment. One is developing the shape. And I call this macro geometry. You'll understand here why in a second. But this basically determines the outer shape of the component, maybe of the assembly. And there's lots of capabilities that we've had here for a while. There's some new capabilities here as well. So parametric modeling has been around for a while. Direct modeling, allowing you to push and pull geometry directly as opposed to working through features and parametrics, which is what you have with parametric modeling. And then subdivision modeling. That's a new one that has become more widespread recently, where you can kind of progressively add controls. It's kind of like direct modeling, but with a little bit more organic control. So that's one of the kind of levers that mechanical engineers can pull. Another one is micro geometry. Now, to date, there hasn't been a whole lot of control for mechanical engineers here. Basically this has been a lot of solid components or solid geometry. And you could get down to micro geometry if you really wanted to model very small details, but that could get very taxing on the computer-aided design software that you're using. And the computer hardware that you're using, that can get taxing very quickly. So you can get into lots of performance issues. But today it's mainly just solid geometry or solid stuff that you work with. The last one is material properties. And to date, you have material selection that is basically homogeneous, right? So you have the same material properties in any spatial direction. And you could select one. And of course, there's been lots of advancements with composites and things like that. But in general, there hasn't been a whole lot of control with material properties and microgeometry. It's really the big lever that mechanical engineers have been pulling today to control their designs for components has been this macro geometry, this macro level geometry, and changing and shifting the geometry and controlling what that outer shape really looks like. Okay, so let's stop there and talk about this for a second because, to date, the primary mechanism or lever, this is what I keep referring to it as, for mechanical engineers to kind of fulfill requirements, make sure they hit performance targets, and fulfill costs and all those types of things have been shape, geometric shape. And that's been, limiting. And it's interesting because not only is it just geometric shape, but that geometric shape has been very constrained by how you can manufacture it, right? So if you're using casted components and then machining out of a block or out of a casting component. To control costs, you really are even more constrained. Like 3-axis machining are only applicable to certain scenarios, right? You can't necessarily get in really deep holes. If you want to avoid 5-axis machining for costs, that further constrains you. So, mechanical engineers have been, this has been the reality for a really long time, right? But this is part of this is part of the context that's changing for mechanical designers, actually in all three of these areas. The first big change that we're seeing that's really going to be reshaping mechanical design has to deal with this macro level or macro geometry modeling. If you've been following the industry, some of this is going to be familiar. This is taking the form of, a lot of people are calling it generative design, or topology optimization is another another term that you can use to describe that. So let's talk about that. Just as a quick reminder, we're actually covering 3 different trends that are reshaping mechanical design today. Macro geometry is what we're focusing on right now. And really, generative design is the big change here. So the idea here is that an engineer will provide a lot of constraints and objectives to some people call it artificial intelligence, other people call it machine learning. Basically what this does is this algorithm, this component of computer-aided design software applications, will produce many different design alternatives. It will vary a lot of stuff. Sometimes this is just removing material, like with topology optimization. In other cases, it's using biomimicry algorithms to explore and develop organic shapes. And this produces a lot of alternatives. It kind of explores the design space for the engineer, but the engineer does have to define some basically like a functional design. What are the constraints? What are the things that govern the outcomes or the output of this effort? Let's talk about macro geometry modeling for a moment, or generative design. Really interesting technology, very innovative, come up with sometimes wildly organic shapes that people would never have thought of before. We're seeing more and more capabilities emerge around taking cost into account, as well as manufacturing constraints, whether it's going to be casted or machined, and things like that, or use additive functionality, which can enable a lot of these wild shapes that we're looking at. And this bodes for a really interesting future for mechanical engineers. I could almost see eventually, at some point, the mechanical engineer being almost a manager of a series of agents that are going off and exploring different design alternatives, maybe on lots of different designs simultaneously. You pair that with a voice assistant, gets pretty interesting. You also pair that with augmented reality, and now you have a completely different interface for what traditionally has been computer-aided software applications. So there's a ton of potential there, but that's kind of that's actually the most mature of these 3 areas that we're going to be talking about in this series for macro geometry modeling. The other one's micro geometry modeling. Is just coming online, or becoming more available now, and material properties as well. So let's talk about those. All right, now let's shift gears and talk about micro geometry modeling. This is a pretty fascinating one. Now, we talked about macro geometry modeling before, which is enabled by generative design and topology optimization, as well as a lot of the other existing modeling methods today. But right now we're going to be talking about micro geometry modeling. And to date, it's really been focused on solid geometry. So the idea here is you can leverage or define lattices from different shapes. You can define mathematical types of definitions for the geometry. And based on that, you can define along with it, you can actually define different volumes or different geometric pieces that will be filled by these lattices, by these mathematical definitions. And there's all sorts of controls that are coming with this type of technology. It's not just fill this volume uniformly with some type of geometry shape. You can define how that varies in different directions, X, Y, or Z. You can have it be random. There's all sorts of mathematical definitions that you can use to power this. All right, so what are the implications of this concept of microgeometry modeling? Well, this is a lever mechanical engineers haven't had before. In earlier discussions, I talked about the outer geometry, the macro geometry modeling was really the only real lever mechanical engineers could pull. Material selection, yeah, sure, to an extent. But this micro geometry modeling, it opens up a whole new avenue. You could have the same outer shape, but model it 10 different ways on the micro level with different lattices, and they could have wildly different performance and still have the outer same look and shape and feel and aesthetics. And this really opens up a brand new avenue of control for mechanical engineers to affect performance, to fulfill requirements, while maintaining all sorts of other things like outer fit. So this is a big deal. This is kind of one of the areas where there's a big game changer in terms of technology that is emerging that can really affect how mechanical design, what it looks like going forward. Next up, we're going to talk about material properties. This is a front that's seen some real innovative progress in the last few years, last 5 years maybe. And it's an area where, combined with additive manufacturing and some other manufacturing methods, can really be leveraged to tailor material properties to fit instead of affecting macro geometry. So let's dive into that. Now, as part of this series, we have covered macro geometry modeling and micro geometry modeling, but now we're going to be focusing on material properties. Now, the idea here is that an engineer can actually specify how material properties change according to a function or equation, and use that in combination with additive manufacturing. So the idea here is you can have the material properties change in according to a certain axis within your part. You could change it with multiple axes, or perhaps even vary it with respect to different equations or formula. Say within certain constraints or within a certain geometric area, like a sphere, the material properties could be different than an outer one. So this is manifesting in a lot of different ways. You see 3D printers now with multi-material printing, where you can have multiple materials within one component. We are quickly approaching the time when you could mix different powders, and the different powders have different material properties, and when you mix them, you get new composite material properties. So with additive manufacturing, it's really opening up a whole new world of capability there. So what does this mean for mechanical design? Well, alongside microgeometry modeling, this is now another lever that mechanical engineers can pull to affect requirement satisfaction and performance issues. You can actually have the same exact shape. You can even have, not include any microgeometry modeling, like with lattices and stuff like that. You have this same exact shape, vary the material properties along its length, or maybe in its center. Maybe make it harder, maybe make it softer, and dramatically affect how the exact same geometric shape has different performance properties: stiffness, deflection, natural frequency, all these outcomes that you really care about when it comes to mechanical performance. Okay, so far we have covered macro geometry modeling, micro geometry modeling, and material properties. Let's talk about the implications of all these new advances and what it means for the future of mechanical design. These three new capabilities that we talked about really can have a drastic effect on mechanical design. With macro geometry modeling, we talked about a new capability in generative design that will automatically produce new design suggestions and alternatives. If paired up with a voice assistant and augmented reality, then mechanical engineers could basically be leading a whole team of agents, software agents, that are doing a lot of the design exploration for them. Another lever that they can pull now is microgeometry modeling, where you can have the same exact shape, but you can have lattices and other types of mathematically defined geometry deliver dramatically different performance and requirement satisfaction for the same exact shape. That is also true with the advances in material properties. Being able to specify how material properties vary spatially and geometrically can also let the mechanical engineer define how the same exact shape can have dramatically different performance, but with different materials. Big advances on all fronts and are positioned to dramatically affect how mechanical design looks like going forward. All right, that completes our series on the 3 technology advances that are reshaping mechanical design. If you found this series valuable, make sure to subscribe or follow us. And that's it. Take care and talk soon.